Much of what we're going to talk about today is review from Algebra 2. You might be feeling now like we do a lot of stuff we did in Algebra 2. So sometimes we'll say like pre-calculus is kind of like Algebra 2 on steroids. Just the same things you did, but more, right? And we're going to see that today. We've already done this in Algebra 2, but here's maybe a little extra something we're going to add now that we're in pre-calculus. Okay, so you're building on the foundation you made. So you have already found zeros of polynomials in Algebra 2, and we're going to look at some of those same ideas today. We're going to start with something called the fundamental theorem of algebra, which the fundamental theorem of algebra is included in the Algebra 2 textbook. So last year you talked about the same theorem. So most important, we don't just want to copy things down into our notebook. We want to make sense of what this says mathematically. We all are mathematicians. We should be able to read these statements and figure out what they're saying. So I'm going to start with the if statement. If f of x is a polynomial of degree n, where n is greater than 0. So what's the first degree we're talking about? Degree 1. Okay. What do we call polynomials of degree 1? Linear. So we're talking about linears, quadratics, cubics, quartic, quintic, 6th degree, 7th degree, so on and so on. What degree are we leaving out? Degree 0. And degree 0 is defined as the constant function. Think about the picture of the graph for the constant function. It was a horizontal line. Okay, so we're leaving out the horizontal lines, and we're starting with the linear lines that have slopes other than 0. So it says, if the polynomial of degree n where n is greater than 0, so we're talking linears and up, then the function f has at least one 0, one or more, in the complex number system. And what types of numbers are in complex number system? Real numbers and imaginary numbers. So this is saying, if you're not a horizontal line, your polynomial is something greater than 0 for the degree, then you will have at least one 0 that is real or imaginary. That's all that says. Linear factorization theorem. Notice that the linear factorization theorem starts off with the same statement. So again, all this is saying is, let's clarify, we can't include horizontal lines. Horizontal lines are a special constant function. They're not going to fit these two statements because of the nature of the graph. So we're talking about linears, quadratics, and up. If the polynomial of degree n where n is greater than 0, then f of x has n zeros and n linear factors. And n is what? The degree. So the zeros is equal to the degree. The number of zeros is equal to the degree. Maybe write that down in your own words. Number of zeros equals the degree. It also means if you want to write that polynomial in factored form with linear factors, so all the factors are just x to the first as the highest degree, then you would have exactly that many factors. If the degree was 5, then you would have to have 5 factors that are linear. If one was quadratic, then you would only have 4. Okay? But this is talking about linear factors. Okay? So here's a quick example of what that looks like. If f of x has the zeros 0, -3, 2i, and -2i, then write the linear factors of f of x. So I'd start by saying f of x equals, and then I take one zero at a time and I decide what its linear factor would look like. If we get 0 as a solution, what does our linear factor look like? It's just x. You can say x minus 0 if you want, but x minus 0 is just 0, and so it's really not necessary. If -3 is a solution or a 0, then what does my factor look like? X plus 3. If 2i is a solution, my factor looks like x minus 2i. The rule doesn't change. It's still like x minus k. And then for -2i, I would have an x plus 2i. So I would have to have 4 linear factors for my 4 zeros, which means what's the degree of my polynomial if I were to distribute all those things? Degree 4, quartic polynomial. Now, notice that you have these imaginary pieces in the linear factors. Totally okay. If I FOIL these out, these are conjugates. So it's going to come out to be x squared plus 4. That's how you would get an answer of plus or minus 2i. But we're not going to write out the one with the real because is this a linear factor? No, it's a quadratic factor. So it's okay if you're asked to write linear factors to leave your complex numbers as complex. Or sorry, your imaginary solutions as imaginary there. Okay? This should help you out when you get your quiz back at the end of class. If you missed that question on the second page about linear factorization, your answer should look something like this, where there's just a bunch of factors that are getting multiplied together, and they're the things you would multiply together to get the original problem. So you have to include all the factors. That's all that question wants from you. Okay. Moving along, we're going to talk about the rational zero test. Yes, sir.
So basically, for the linear, you write it as you would write something in a linear form, x plus something.
Yes, we think the linear factor, when I say linear factor, you think x minus k.
Okay.
And it's usually like you assume that it's a minus, so everything changes signs because you're going to do inverse operations to solve.
The plus functions.
Mm-hmm. Now, if you had a 0 of like 1/2 as a side note, that would be like x minus 1/2. But we usually see that when in factored form is 2x minus 1. Because then you'd add 1 and divide by 2, and that's how you got the -1/2. So the fractions you kind of adjust a little bit. The denominator goes in front of the 2, or in front of the x. Okay. This is, and should sound very familiar from Algebra 2. In Algebra 2, it has a different name. It's called the rational root theorem. Roots, zeros, solutions, synonyms.
There's so many different words for it.
Well, because in some cases they mean different things. But in a lot of cases they could be used interchangeably. if f of x is a polynomial with integer coefficients, so that would mean when you're looking at your coefficients to all your terms in your polynomial, none of them are irrational, have radicals, none of them are imaginary. Okay, they have to be rational, or sorry, integer coefficients, no fractions. Then every rational zero of the function would be in the form p over q. Okay, and we have to describe what p over q actually means. So in terms of p over q, we're saying p and q have no common factors. So that basically means as a rational solution, it's simplified. You're not going to see 6 over 8. You're going to see 3 over 4. Okay, so you've reduced them. Okay. So they share no common factors, and p would be a factor of your constant term in your polynomial. That would be the term at the end of the polynomial that has no x, because no matter what you put in for x, it always stays the same. It's unchanged, so it's constant. And q is a factor of the leading coefficient. So remember, the degree is the highest exponent in your polynomial. The leading coefficient is the number that's multiplied in front of the term with the highest exponent. Does this sound familiar? Factors of your constant over factors of your leading coefficient? P over Q? It should be. This is great because if I don't give you hints as to like verify this as a factor or knowing this is a zero, you can now find all the zeros of a polynomial using the rational zero test. So we're going to see an example where we do that. Okay, I'm going to give you a polynomial f of x, and then I'm just going to say, find the rational zeros. Okay. So here I say, f of x is 2x cubed plus 3x squared minus 8x plus 3. In section 2.3, I would have followed up with something saying like, verify that x plus 2 is a factor. And then you would know where to start synthetic. Okay? But here I'm just saying, tell me what the zero is, or what the zeros are, and that's all the information I'm going to give you. So we usually start with a list of possible solutions. So I'm going to say possible rational zeros. Oh yeah, fun times. And you make this list of possible rational zeros using that rational zero test from the last slide. So we need the p's and the q's, which are factors of your constant. What are factors of your constant term? 1 and 3. Okay, these are going to be your p's. And factors of your leading coefficient, 1 and 2. And we want to set them up, remember, like p over q. So we're going to take 1 and 3 separately, and we're going to put them over 1. What else did you do when you made the list? Cried? No. Tears of joy, maybe, from the fun. You usually add a plus or minus. You don't know if it's going to be positive times positive or negative times negative. So you just include the positive and the negative. So my first one would be P is 1 and Q is 1. 1 over 1 is 1. That's easy. And then my next P would be 3. I should also put that over my Q of 1. 3 over 1 is 3. And then I've got to go back. I'm going to take those and put them over 2. So 1 over 2 and 3 over 2. And these numbers are all rational. They can be written as fractions, and they are the possible rational solutions. I have 4 positive and 4 negative that I could check. Because that's degree 3, how many total solutions should I have? 3. Okay. Now, not all of those solutions have to be rational. Some of them could be irrational or even imaginary, and they're not on that list. Okay, so the only things I'm finding on this list are rational zeros. Well, you should have cried tears of joy, because now that you have this list of 8, instead of checking infinitely many numbers, you have just a section of 8 to choose from. So you're going to start what we would maybe call, and you guys were kind of bringing up in a chat the other day, synthetic guess and check. Yay. And it's fun because what are you looking for at the end? Remainder of 0, happy faces. Everybody should have a happy face right now. No? Okay, now you can check in any order that you want. I am an orderly person. I always go in order. I check positive 1, then negative 1. I check positive 3, then negative 3. Positive 1/2, then negative 1/2. That way I know what I checked. I know there are students out there that like to just randomly choose, like a game of roulette, and see what they find. I'm going to choose 1. Add down to get 2, multiply, add down, multiply. Oh my gosh, I'm so lucky and happy. I found 1. It worked. Will you always find out on the first try? No, but that's okay. So the the possible rational 0 of 1 actually works, so I should list that in my zeros. Can I search for more rational zeros? Yes, what are the methods I could use to find more rational zeros? You can keep doing synthetic guess and check if you want. Or Jennifer says you can factor out the quadratic that you just made with synthetic division. Of course, I'm going to say whenever you get to a quadratic, try to solve it by factoring your quadratic formula. That way you'll know instantly if you have more rational solutions. Mason, were you going to add something there?
If we tried 1, should the 0 be negative 1 instead of 1? Or...
No, because remember that if you had put 1 on the outside of synthetic, what did the linear factor look like? X minus 1. And if x minus 1 was your linear factor, then x minus 1 equals 0 would produce a positive 1 solution. Yeah, so you only have to change the sign when you get it in the linear factor. Okay, I like to use guess and check for factoring. So I make 2 groups of parentheses, and I always start with my very first term. What would I have to multiply together to get 2x squared? 2x and x. If I have something that's not prime, like 4x squared, I have to remember it could be 4x and x. It could also be 2x and 2x. That's part of my guessing and checking. In the back there, I've got a negative 3. I always go to my last term. What do I multiply together to get negative 3? Negative 1 times 3, negative 3 times 1. I can kind of play around with those. Again, this is part of my guess and check, right? So maybe I'll just throw 1 in. I'll do like negative 1 and positive 3. Okay, and I'll check it. Well, I'd get 2x squared and I'd get negative 3, but I got to check outsides and insides. This would give me 6x minus 1x. Oh, I got it right again. Look at me. I didn't mean to. I was trying to get it wrong. Okay, so we have it correct. Okay, it's positive 5x, it's negative 3. And do these then produce more rational solutions? Yeah. 2x minus 1 equals 0 will give me an x of 1/2, and x plus 3 equals 0 will give me a 0 of negative 3. So I can add those to the list. The last thing I would point out to you is if you look back at your list of possible rational solutions or possible rational zeros, we found additional 1/2 and negative 3 are those numbers on that list. Yes, so like Jennifer had originally said, I could keep doing guess and check. I would have eventually found them. It maybe would have taken more time because I might find some that didn't work in between. Are we all okay with this? You remember it and you love it. Okay, good. I'm glad to hear that. You look really excited. It's awesome. And we could also from there like write out linear factorization. We have all the zeros. There's only 3 of them because it's cubic. Oh, and someone told me last hour I have a typo here. If a plus bi is a 0, then a plus or a minus bi is also a 0. I had an extra a that they didn't like. In your own words, what is this telling you? Complex conjugates are always zeros together. I love that. If you want to write that down in your own words, or Sammy's words, write that down. Complex conjugates always come as zeros together. Can you ever have just one imaginary solution? No, because it comes with its partner, right? And that must always be true. Okay? So if a plus bi is a 0, then a minus bi is also a 0. Here's an example then. We want to write the polynomial that has the given zeros 0 and 2 plus I. Are those the only zeros of the polynomial? No. The other 0 must be 2 minus I. So always remember, if I only list one imaginary solution, you can say that the other one must be a 0. So if I have 3 zeros, when I write my polynomial, it's going to be what degree? A degree of 3 at least. Okay, assuming these all have multiplicity of 1 there. So I'm going to write out the linear factors. They'll look something like this. X for 0, x minus 2 plus I, but I really want to subtract that whole complex number, 2 plus I. To subtract that whole complex number, I'm going to put it in parentheses. And then we'll have x minus 2, oh, this one was plus, and I'm going in order, 2 minus I. And then to write the polynomial, you could go back to like graphing exploration. I showed you how I would do part C, which is distributing the negative, regrouping, and FOILing it back out. Or we can use Mason's method to write the polynomial. So if we wanted to multiply or figure out what are these things multiplied together, knowing that 2 plus I and 2 minus I is a solution, how would you start using Mason's method to write that? X equals what? He did it with 1 plus the square root of 3 and 1 minus the square root of 3. Do you remember how you rewrote it? You said X was equal to 1 plus or minus. So we could write this as 2 plus or minus I. It seems like in that rewriting, you guys preferred his method over mine. So I'm going to show you his method works with complex numbers too. The idea here is we want to say, like, what if these were the solutions we got? What did it look like if we solved backwards? So remember, the number in front of plus or minus should go to the other side. So we're going to subtract 2 from both sides. X minus 2 equals plus or minus I. What would we have done in solving to get that plus or minus I? You would have taken the square root of a negative number, which would have produced a plus or minus I. What will we do that's the opposite of a square root? Square both sides. On the side with x minus 2 squared, remember that's x minus 2 times x minus 2, so we're going to get x squared minus 4x plus 4. And then what is I squared? -1. And you can start to see here we're forming that quadratic that would have produced the solution 2 plus or minus I. Finally, add 1 to the other side. So x squared minus 4x plus 5. In Mason's method, we really still have an equation like equals 0, and that's because we're doing like the opposite of solving for an x-intercept. You can kind of at that point drop the equals 0, and this is the quadratic that has the solutions 2 plus or minus I. Okay. So these two factors multiply, distribute to get us this quadratic. We still have to do what? To get our final polynomial. Multiply it by the x. Okay, so we're saying f of x is really equal to x times x squared minus 4x plus 5. Okay. So f of x is equal to x cubed minus 4x squared plus 5x. Okay, so that workaround, if you like that method of kind of like thinking about a solving problem backwards. So it's like you're redoing all the things that you would have done to solve. If you don't like that method and you want to see my method again, you could stop in before after school and see me. I'd be happy to help you with that. Okay, so we have one more example. Use the given 0 to find all the zeros. This is where maybe we've changed things up from Algebra 2. So you probably didn't solve anything like this in Algebra 2. If I gave you a 0 to help you find all the zeros, it probably would have been a real 0. This time I'm giving you an imaginary 0. With a real 0, we could just pop it into synthetic and then factor what remains. Okay. Here, we don't really have that option with the imaginary 0. So if -1 minus 3i is a solution, what else do you know? -1 plus 3i is also a solution. If you just...
So you wouldn't make the -1 into a positive?
No. Conjugate is only changing the sign in between a and bi. If you know those two imaginary solutions, then you can find the quadratic factor. What we just did. Okay, so let's set x equal to -1 plus or minus 3i. What are you going to do to make that into a quadratic factor? Add 1. X plus 1 equals plus or minus 3i. Square to get rid of that plus or minus. X plus 1 squared is x squared plus 2x plus 1. What's 3i squared? -9. Be careful if you said -3, you have to distribute the square to the 3 and to the i. 3i times 3i. 9i squared, -9. And so the quadratic factor is x squared plus 2x plus 10. Remember, there's that equals 0, but we can kind of drop it. So this is a factor. If you know a quadratic factor, then you can do long division to find the missing factor and find the other zeros. Okay, so we're going to set up a long division. X cubed plus 4x squared plus 14x plus 20. Sorry. If you know this is a factor, what should happen in your long division? Sorry, what? It should go out evenly. You should get a remainder of 0. Okay, so it should work out pretty nicely for you since you've found something that is considered to be a factor. So we're going to start saying, what would I have to multiply x by to get x cubed? X. So we're going to put that above the 14x right over here. Distribute to all terms, x cubed plus 2x squared plus 20x. We are really
What did it be?
subtracting. What did it?
be 10x?
Yes, 10x. I was like, something's not right. Thank you. That's 10x, and then it would be minus 10x, right? Good. The x cubes will cancel. I'll get 2x squared plus 4x plus 20, and then I just repeat the process. What would I have to multiply to get 2x squared? A 2. I'll put plus 2 up here. Distribute, that gets me 2x squared plus 4x plus 20. There's the 20 I wanted. And that's going to cancel out, right? When you subtract all those things, so you're feeling happy. And this is your missing linear factor that would get you that cubic polynomial. What is the 0 that comes with that? Negative 2. If you set x plus 2 equal to 0, then you get x equals negative 2. So when it says find all the zeros, you know the conjugate, and you know negative 2. So you have all the zeros there. I forgot to pick up your warm-up sheets and your problem sets, right? Will you pass those forward, and the person at the front of the row can make 2 piles for me? You're getting your quiz back? You're going to make corrections to this quiz like you did for the last one. You need extra practice. Some have a few things to check, nothing to check. Some have more. These are old, I apologize. This is going to be due on Tuesday. Can you write that at the top of your quiz? Due on Tuesday?